This podcast focuses on real field problems faced by inspection, corrosion, and integrity professionals, explains why they happen, discusses what actually works in practice. No theory for the sake of theory, only field reality.
Welcome to this technical deep dive into the compressor performance engineering. In this video, we will break down how compressors actually work from thermodynamic principles to real-world performance calculations. We will explore how pressure, temperature, and gas properties interact and how these directly impact power requirements. But more importantly, we will simplify the complexity so you can understand not just the equations, but the engineering intuition behind them. Whether you are sizing a machine or analyzing efficiency, this is where theory meets application. I am Chandan Chattopadhyay, Process Advisor, and let's get started. Compressor performance doesn't start with the machine. It starts with the gas. Three properties define everything. The compressibility factor Z, the ratio of specific heats, and K, the molecular weight M. Together they determine how the gas responds under compression. Now, at the inlet, we standardize flow as cubic meter per hour, but this is not fixed. It shifts with elevation, humidity, and gas composition. So, what looks like a simple flow number is actually a moving target. And understanding that is the key to accurate compressor design. Once again, everything comes back to one parameter, the polytropic exponent N. It is not guessed, it's solved iteratively by reconciling pressure and volume behavior through the compression path. And once you have N, you unlock the next critical outcome, discharge temperature T2. Because T2 is not arbitrary, it is governed by the inlet temperature T1, the pressure ratio, and the nature of the process captured in N. So this step is not just math. It's where prediction becomes engineering reality. Now we quantify the work of compression through head. Two forms matter here, isoentropic head HS and the polytropic head HP. Different paths but built on the same foundation, compressibility, gas constant, and inlet temperature. They describe how much energy the gas actually absorbs during compression. But in reality, no process is perfect. That's where efficiency comes in, linking the ideal isoentropic case to the real polytropic behavior through a single governing relationship. So these heads are not just numbers, they are a direct measure of performance. Now we arrive at the number that truly matters, power. Gas horsepower or GHP represents the real energy required to compress the gas before mechanical losses come into play. In centrifugal compressors, this is governed by polytropic efficiency, typically in the range of 63 to 77%. And the relationship is straightforward. Mass flow multiplied by polytropic head adjusted by efficiency. So GHP is not just a calculation, it is the direct link between thermodynamics and the driver you ultimately select. Now we move to protection, because performance means nothing without stability. Antisurge control tracks the compressor against its most dangerous boundary, the surge limit line. But instead of raw values, it uses invariant coordinates, reduced flow and reduced head. Reduced flow comes from pressure behavior. while reduced head incorporates temperature and the polytropic exponent. But why this matter? Because these parameters remain consistent even as conditions change, and that's what allows the system to react in real time, preventing the destructive onset of flow reversal. This is not just control, it's protection at the edge of instability. In case study 1, we test the limits of a single-stage centrifugal compression in pipeline service. The key question is thermal. How hot does the gas get? The result, a discharge temperature of 127.5 degrees Celsius. That's critical because industry practice sets a practical threshold around 150 degrees C. Stay below it, and a single stage decision remains viable. Exceed it and you are forced into staging or cooling. So this is not just a temperature number, it's a design decision. Now consider case study 2, hydrogen makeup surface. At first glance, it looks similar, a single stage compression scenario. But hydrogen changes everything. Because of its thermodynamic behavior, the discharge temperature does not just rise, it skyrockets. The result, 404 degrees Celsius. That's not just high, it is far beyond the API 618 recommended limit of 135 degrees C. And at that point, you are no longer talking about performance, you are talking about risk. Structural integrity is compromised. Lubricating oil begins to carbonize. Reliability drops fast. So a single stage design here is not just inefficient, it's fundamentally unsafe. And that's where engineering judgment overrides simplicity. So, how do we solve the hydrogen problem? We don't fight the physics, we work with it. Instead of a single stage design, we move to 3 stages with intercooling in between. Now the compression is distributed, the ratio per stage drops to just about 2.08. And that changes everything, because with cooling after each stage, the temperature rise is reset again and again. The result? Discharge temperature falls back into a controllable range close to API 618 limits. So this is not just a design upgrade, it's a shift in strategy from pushing the machine to a managing the thermodynamics. When compression ratios climb, single stage solutions reach their limit. That's where multi-stage design becomes essential. A 3-stage configuration with intercooling breaks the process into manageable steps. Each stage handles part of the pressure rise, and each cooler removes the heat of compression before it can accumulate. And to that, interstage scrubbers removing condensed liquids and protecting downstream equipment. Because it is not just about pressure, it is about controlling temperature limits, mechanical stress, and preventing oil carbonization. So multi-stage is not complexity for its own sake, it is how we make compression sustainable. Multi-stage summary highlights T2 control for reciprocating machines. The ratio strategy to balance compression ratios across stages and API compliance, where API 618 limits prevent lubrication failure, restricting hydrogen service to 135 degrees Celsius. This section covers industrial compressor dynamics, focusing on aerodynamic versus mechanical compression limits, surge vulnerabilities, and capacity regulation, referencing API 617 and API 618 standards. The two main machines types are dynamic centrifugal, which is aerodynamically limited, and positive displacement reciprocating, which is mechanically limited. The primary threat for dynamic machine is surge, while for reciprocating machines it is mechanical and thermal stress. Compressor selection isn't arbitrary. It lives within a landscape defined by two-axis flow and head. At low flow and very high pressure, reciprocating compressors dominate. They deliver extreme head but at limited capacity. Move across to higher flows and centrifugal machines take over. This is the broadest operating region designed for continuous, stable performance across a wide range. Push further into ultra-high flow, low-pressure territory, and axial compressors become the solution. And then there are rotary machines filing niche application where specific design constraints apply. So this chart is not just classification. Surge is not a single event, it's a cycle of instability. It begins at the surge line where the compressor reaches its aerodynamic limit. Push beyond this point and the system can no longer sustain the pressure rise. Phase 1 stall, flow drops below the minimum required. Phase 2 deep surge, the flow does not just weaken, it reverses violently. Then comes the phase 3, pressure collapses downstream or builds at suction, destabilizing the system further. And finally, recovery, flow resumes briefly until the cycle repeats. This entire loop can happen in seconds, but the damage can last much longer. That's why compressors are designed with surge margins and control systems act early before instability begins. Surge does not just affect flow, it hits the machine itself. And the most vulnerable component, the axial thrust bearing. Because surge is symmetric, but the forces it generates are not steady. They reverse violently. Under normal operation, axial forces remain stable around 35 newtons in this case. But enter deep surge and those forces don't just increase, they oscillate, spiking to over 100 newtons back and forth at a frequency of about 2.5 Hz. That's not load, that's hammering. A continuous cycle of thrust reversal, pushing and pulling on the rotor assembly. And over time, this is what leads to wear, damage, and ultimately failure. So, surge is not just aerodynamic problem, it's a mechanical one at the core of the machine. Surge is not just a compressor problem, it's a system problem. and one variable dominates everything: downstream volume. The volume between the discharge flange and the check valve directly controls the surge behavior. In fact, surge frequency is strongly dependent on this volume and only weakly influenced by rotational speed. Now, here is where it gets interesting. As you reduce downstream volume, the system does not become calmer, it becomes more unstable. Surge frequency increases sharply from as low as 0.25 Hz to as high as 3.5 Hz. At the same time, axial forces rises significantly. So the machine is no longer experiencing slow, occasional disturbances. It is being subjected to rapid, repeated mechanical loading. This leads to fatigue, especially in critical components like thrust bearings, which challenges conventional thinking. Because smaller volumes may seem safer, but in reality, they create faster, more damaging surge cycles. So in compressor systems, volume does not just define space, it defines stability and risk. The surge severity coefficient gamma evaluates causative energy versus restorative energy. A value greater than 0.01 indicates deep surge, suggesting high potential damage and catastrophic thrust failure. Positive displacement compressors shift to mechanical limits. They do not experience aerodynamic surge, but instead face severe mechanical stress known as rod loading and thermal limits restricting discharge temperatures to 135 degrees Celsius per stage. The capacity control challenge for positive displacement machines is that flow is constant per stroke. Capacity must be controlled volumetrically, typically through clearance pockets or variable speed operation. Capacity control in reciprocating compressors is not continuous, it's discrete and highly engineered. This is a 5-step unloading architecture. At full load 100%, the machine operates in normal double acting mode. Then we begin unloading. At 75%, we open the head end clearance pocket, reducing effective compression volume. At 50%, we go further, activating the crack end valve unloader. Now the machine is partially bypassing compression valve. At 25%, both mechanisms combine clearance pocket open and valve unloader active. And finally, at zero load, both ends are unloaded. The system alternates sides periodically to prevent temperature buildup. No recycling, no wasted energy, just precise stepwise control of capacity built directly into the machine. Compressor startup is not a switch, it's a controlled sequence. First, utilities and purge, ensuring the system is clean and warm. Then, barring and jacking to safely prepare the rotor. Next, lubrication, critical but time bound. Delay too long and you risk oil accumulation. And finally, zero load start with bypass open, building pressure gradually. Each step is a safeguard because a safe start is not optional, it's engineered. We have explored compressor performance from thermodynamics to control to real-world limitations, and what emerges is clear. These machines are not just equipment, they are governed by physics, constrained by design, and defined by how well we understand them. I hope this journey has helped you see not just the calculation, but the engineering behind them, and more importantly, the intricacies that make compressor performance both challenging and fascinating. Thank you for watching.
That's today's EIM Technical Talk. If this episode helped you, follow the podcast and share it with your inspection or corrosion team. If you want structured support in inspection, corrosion, or asset integrity decision making, EIM also runs mentoring and technical programs. Details are in the description. Send us your field problems and we'll cover them in upcoming episodes.